Thanks a lot. I think it's awesome to just get together like this. You're all very dedicated for climbing 6 stairs or taking the lift, so I'm very happy that you're here. So I'm going to talk about deep learning for more than speech recognition. I'm a lecturer at E&E Engineering in Stellenbosch University. Before I start, I think Jock already covered some of this, but I just want to have an idea. Are you engineering people, computer science people, applied mathematics people, or other people? So just the engineers, electronic engineers, CS, computer science, awesome, applied maths. Okay, other? What's the other? Physics? Neuroscience? Statistics, of course, but you're basically doing applied maths. Sorry. Okay, that's great. And just very quickly, I know there's a bunch of Stellenbosch people here who have seen me talk before. I mean, I don't talk that much. Well, I talk a lot. Okay, so I hope you guys aren't bored. The rest of you will probably find this interesting. Okay, so I'm going to talk about deep learning for more than speech recognition. Speech recognition, really over the last couple of years, Jock just mentioned that it started reaching levels of performance we can actually use these systems. Okay, 5 years ago, no one did Google voice search. Now I can go on my phone, I can say, okay, Google, what's the weather in Cape Town, right? And it answers, okay? And it's really an exciting time. It's a great time to go to speech conferences. So Microsoft made headlines. This is 2016. This is their paper on archive. It's a great time to go to speech conferences. Microsoft will present their paper and say, oh, we're reaching human levels of accuracy. Some guy from IBM will stand up and say, no, you're not. You evaluated wrong. Big argument, conflict, excitement, right? So I really like conflict as long as I'm not involved with it. But it's an exciting time for speech recognition. Okay, so that's what I'm going to talk about today. A quick outline of my talk. I'm going to talk about 3 things. First, I'll just quickly, I mean, it's impossible in an hour to cover state-of-the-art speech recognition, but I'll give you a flavor of maybe a little bit of the history and how state-of-the-art systems are built, okay? Then I'm going to start to rant a little bit. Specifically, I think speech is so much more than just speech recognition. And I think people need to get interested in the interesting parts of speech. I think it can tell us a lot about us, about what goes on in our minds. So in the second part of the talk, I'll give a quick overview of some very interesting work in speech that doesn't actually use speech recognition. And I think that's very exciting. So that will be rant number 1. And then for rant number 2, I'll talk a little bit about the work that we're doing at Stellenbosch in our group. Okay, so let's get going. State-of-the-art speech recognition. So this is how Google built their speech recognition systems. They get tons and tons of spoken audio. Okay, they record it, plug it onto their monster server, and then they get some poor guy to sit down, some poor guy in an office, and actually transcribe the speech. So you will have the speech waveform and then the words that's being said in the speech. Okay. And normally you just you've got a sentence and you annotate it at the sentence level, so you might not know exactly where this word occurs in the speech, but you've got a rough idea. Okay. So you've got input, which is speech, output, which is words. So what would you do? You guys know, right? You just train a model, okay? A supervised machine learning model that takes in the audio and pops out the words. Okay, and boom, we've got OK Google on our phones. Okay, just nod if that makes sense. Yeah? Okay, so we're done, right? I don't have to talk about anything else, right? You're a machine learning expert. Okay, I'll talk a little bit more. Okay, so there's definitely more involved than just training models. Okay, so the first thing we need to do, sorry for the E&E guys, this is going to be a bit boring, but the first thing you need to do is you need to convert the speech into some form that you can actually use. So this is a very long, one-dimensional signal. It's actually quite hard to process, a lot of data. And we know something about speech. We know that what makes speech speech is really not the time domain signal, but it's really the frequency contents, right? So if you look at a bit of a speech, it's really like the sound of that bit of speech that makes the signal. So most speech recognition systems, including the Google systems, they would start by extracting features from the speech waveform. So So here's the raw waveform. And what we do is we say, let's just take a small snippet of that speech. Okay, 25 milliseconds. That's the typical duration of something like a phoneme, the shortest unit of sound. Okay, we take that window, and what we do is we look at the frequency content in that window. Okay, and we represent that as a little vector. Is this thing bouncing up and down, or is it just me? Okay, I'm not going crazy. Let's go and talk on this side. Okay, so you take that bit, and you look at the frequency content in that bit of speech. And this you represent as a vector. Okay, and then what you do is you move along, you take the next window, get the next vector, and so on. Okay, so you're transforming that one-dimensional signal into a two-dimensional signal, where each one of these values tell you something about the frequency content at the specific frequency. Just nod if that makes sense. Okay, so you guys are intelligent, okay? So for the engineers, think fast Fourier transforming, all right? Okay. And then what we do is sometimes you do some post-processing on these features to get your ultimate vectors, but you end up with a sequence of vectors that you're going to use. You can actually look at these vectors. This is what they look like, 2 words. So here we've got the time dimension here, and we've got the frequency dimension here. So this is like the vectors stacked next to one another. Just not if you've seen a picture like this before. Okay, engineers, this is spectrograms, short-time Fourier transform. For the rest of you, it's not super important, but these things are pretty cool. Okay, so this is a single word spoken by 2 speakers. And there are some people that can look at these things and actually read it. So I can't do it. I can tell you some of it. So here we've got a lot of high frequency content. Can anyone guess what sound that would be? Right? It's got a lot of high frequency content. Okay? So here's what's this? This as well. Okay, right. Here we've got a silence. Here we've got a very short silence followed by some energy. I don't know what that is, but it's probably a b or a k. So those sounds are characterized by a short stop, a short silence, followed by a burst. So it's sometimes called a plosive. You've got something similar here. Okay, great stuff. There's people that can really read these things. It's amazing. What do you think these things are? You've got them here. So I've covered most consonants. They're vowels, right? So actually the word here is encyclopedia. And I think this is I that goes here. I. Okay, pretty awesome. What's the difference between these two? So at the rough scale, they follow a very similar trend. Okay, and you can see kind of here you've got this raise, here you've got that raise. What's the difference? Just very quickly. Yeah. One exactly right. So you said one is male, one is female. Which one is male? The lower one. Why? Right. So you've got these. You've got the same trajectory, but these things are stacked much closer together, and male speakers have a lower pitch. Okay. Awesome. Okay, we're done. We've got our vectors. Google is happy. They record the audio, convert it to these vectors, and then they boom, machine learning. Okay, and everyone is happy. Okay, so we can stop here. But I'll go on because you gave me more time. Okay, so very quickly, you've got this representation. You're going to feed it into a neural model. We just saw a whole hodgepodge of different neural models downstairs. In your head, quickly think, what neural model do you think would be useful for processing speech? I'll quickly put on the screen a few neural models. Just tell me what the architecture is. Just shout it out. So what's this thing? A recurrent neural network. You can shout louder. If you do fancy stuff inside the A, what's it then? LSTM, right? LSTM is just fancy stuff in there. Okay. What's this model? A feed-forward neural network. Thank you for that one person. Sometimes they just call it a deep neural network, right? But it's a feed-forward. This thing? Convolutional neural network. Okay. Okay, we've seen 3 networks. Which one would you use for speech? Yeah, okay. A lot of answers. Okay, let me tell you what people... Well, last question. What's this network? HMM. So you were born in the 70s, right? Sorry. Exactly right. Sorry. That's exactly right. HMM. Who have seen HMMs before? Okay, that's wonderful. I'm so happy on the inside right now. Okay, so HMMs are really what people used for speech recognition from the 80s to the late 2000s. Okay, people were using HMMs. So I'm going to build towards like which neural model do we use. I'm going to answer that question. But what I'll do is I'll first do a bit of a flashback, right? So we'll first go back to HMMs. And because just half of you know what HMMs are, I'm going to quickly review it. Pay attention because it's got a use. Okay, it's got a use somewhere, even in today's system. Okay, so hidden Markov models are generative models. Neural networks are discriminative models. Class 1, class 2, I'm pulling them apart. That's discriminative. Generative is, this is my class, generate data. Okay, so another thing that a lot of neural network people don't know that much about is probabilities. Okay, so what we'll quickly do is we'll write down the speech recognition problem as a probability problem. And then we'll see how we can solve that using a generative hidden Markov model. I'll go over this fairly quickly. Okay, so what we've got here is, okay, let's just step through this. What we really want to figure out is, if we've got speech features here, those are speech features, what we want to figure out is what words are very probable given those speech features. Okay, so what's the sequence of words that are probable given those speech features? And for speech recognition, really what we want to figure out is what's the most likely word sequence given the input speech. Not if that makes sense. Not if you've seen a P before. Okay, sorry. I just like people nodding. Anyway, so one thing we know about words, right? So now we've got a word sequence here is we know what's the basic building block of words. Written words, it's characters. Spoken words, it's phonemes. So we actually know the pronunciation of words. Okay, so let's put that into our probability equation thingy. Okay, so what we'll do is we'll say a sequence of words have some pronunciations, so without is pronounced in that way. Okay, and we can marginalize out over all those pronunciations. Now I'll go very quickly. We do some, stats people, sorry if this is not right, but I think it is. Okay, so I'll do some Bayes and conditional probability here. So we can convert that. That's just Bayes rule. It's not dependent on X, so that falls away. Engineers are lazy. We don't like sums, so what do? We just take a max. You can do it. Okay. Sorry. Okay, and then you end up with this equation. Okay, so we end up with this equation. Here we've got the density function of the speech features given the pronunciation. So if I know I'm in phoneme in without, then I have a model which tells me how likely is that sequence of vectors that we talked about before, given that phoneme. Okay, that's the first part of a speech recognition system, a conventional speech recognition system, is this thing. Probability of speech given pronunciation. And this is, the hidden Markov model is going to be used here. Here we've got something which is the probability of a pronunciation given the word. So some words are pronounced in more than one way, and we need to model that. That's called the pronunciation dictionary. Okay. The last thing, this is the probability of W. Now remember, W is actually a sequence of words. Okay, so this thing is called the language model. And I think Jacques mentioned this very quickly. The language model basically tells us how likely is a sequence of written words, right? If I say I really like the red car, apple, something like that is very likely. If I say I really like the red run, okay, it doesn't make sense. Okay, so you can model that. Let's go back. How do you train a language model? You go on Wikipedia, you download all the text that you can possibly get, and you model that. Okay, not if that makes sense. So on text data, huge amounts of text data, you can have a language model. The pronunciation dictionary, how do you get that? Do you get the pronunciation given the word? You force a linguist to write it down. Okay, so how many linguists are in the audience? That's actually very sad, but it's fine. I just insulted them, so I'm okay. Okay, and then the last thing is the model which is called the acoustic model, telling us how likely is the acoustics given the pronunciation. And this is the hidden Markov model. That's what that gives you. Okay, now to build a speech system using this approach is super painful, right? I spent like 3 years of my master's doing it. I only took 2 years for my master's. Okay, whatever. So it took me a really long time to build this model. It's really painful because you've got issues here, you've got issues here, and you've got a lot of issues there. Okay, So very painful. Let's quickly look at specifically the hidden Markov model. So here we say, here we've got a little hidden Markov model for the phoneme okay? Hidden Markov model consists of states. Without going into the detail, you can think of it as kind of the start of the middle and the last okay? And you're going to train this on lots and lots of data. One issue is that you don't actually know if these are my speech vectors, you don't know which vectors belongs to which state, okay? So how you solve this is you use an algorithm called expectation maximization. You start with a random hidden Markov model. You align these frames to the states, and you update the state parameters, okay? And then what you do is you go back again and you say, under the new parameters, what is a better alignment of my frames to the states? You update the parameters again. Not if that makes sense. Okay, it's very quick. It's not super important. Now the thing is, to build a speech recognizer, you've got these HMM models for phonemes. You combine all of the different little HMMs for all the different phonemes into a big-ass network. Sorry, I didn't say ass, but a big network, okay? You combine all the little phonemes into words, all the little words into sentences using your language model, and you end up with an enormous, big, finite state machine, okay? And that's how we did speech recognition for a large part of speech recognition, okay? And there's thousands of these states. Normally, we use a lot of states to model a phoneme. There's just 3. You use a lot, so 9,000 states are quite typical in a relatively big system. 50,000 words, okay? And that's big. Very painful, pain, suffering, death, all of that stuff, okay? So not fun. Okay. Let's flash back to today. Very quickly, we spoke about 3 neural networks, RNNs, ConvNets, feedforward. Which one would you use to do speech recognition? RNNs, great option. Okay, so in 2015, William Chan, he proposed this model called listen, attend, and spell, which is based exactly on an RNN. Listen, attend, and spell. I'll go over it super quickly. So the model is basically big RNNs stitched together. And it's got these 3 components. It's in the name: listen, attend, and spell. Okay. So I'll step through the model step by step, and then hopefully it will make sense. So the listen model, basically here at the bottom, we've got these speech features that I've been talking about. Okay. That gets fed into this bidirectional RNN. And then he uses a very cool trick. So the one problem is that if you have 10 seconds of speech, which is not uncommon, this thing is going to be super long. Okay, very, very long, and you need to fit that on a GPU. So pain, suffering, all of that. So he uses this cool trick in his listener where he basically combines some of the states in the previous RNN, and he does this in this pyramid structure. And in the end, he ends up with a whole bunch of hidden vectors from your RNN output. But the number of hidden vectors here are a lot smaller than the hidden vectors, the number of input vectors here. Okay, does that make sense? Okay, so that's what the listener does. Okay, now let's look at the speller, a little bit more complicated. Instead of, we'll go from the output down. Instead of using words as his output, he actually used characters as the output. Okay, and how would he know which characters to output? Well, he would look at, so this thing outputs the listener outputs a whole bunch of vectors. And to know which character to output, you look at all these vectors. Okay. And you say to output the first character, I looked at all my hidden vectors, and really those hidden vectors are a summary of what is going on in the speech. Okay. Given that, I output my first character, and then what he does is, without going into too much detail, he actually takes the output, he feeds that into the next state, and then when he outputs the next character, he actually takes into account the previous character that was produced. Okay, so that's the speller bit. The attend bit is really how we incorporate these models when we generate the character. So it's really nice. What you can do is you basically look at the whole speech segment and you ask which portion of the speech segment is important for me when I'm outputting the first character, the second character, and so on until I get to the last written character for that utterance. Okay, so we've got listen, summarizes things into vectors. Attend, which means I can look at different portions of my summary, and then spell, which produces the output character. I realize this is super quick, just not if you've got the intuition. Okay, so the model looks like this. Okay, and you use bidirectional LSTMs here and there. Okay, one cool thing you can do with this model is when you output a certain character, you can actually ask the model which bit of the input speech did you look at most when you produce that character. So he drew this very, very nice pictures. So here, I don't know if you can read this, but it says how much would a woodchucker chalk, okay? And you can see that for the h in how, basically the model looked at that bit of speech, and in his talk you could actually go and listen to that and see that it is a h sound. Okay, what's great about this? You don't need a linguist. Okay, sorry. Okay, you don't need a linguist because you don't need a pronunciation dictionary. We'll just output the characters directly. Forget about phonemes. Who needs phonemes? Okay. You don't need. Well, you can incorporate the language model in here. The language model is kind of incorporated into the character model already. Okay. So you just need a ton of audio with the characters, and you're done. Okay. So everyone is happy. Life is wonderful. Okay. So why the fudge did I tell you about HMMs? Right. Why, and why does he know about HMMs? Okay, he's born in the 70s, so that's why. But, okay, apart from those reasons, why did I tell you about HMMs? So actually, when the speech recognition systems became very accurate in like 2013, it was not because of RNNs or LSTMs. It was because we got used to training just normal feed-forward neural networks. Okay. Now, if we want to train just a normal feed-forward neural network on speech, it's easy, right? You give it a snippet of speech and you ask it which phoneme or which character is relevant for that bit of speech, okay? And you just sweep your neural network across and you get out your characters or your phonemes, okay? Everyone is happy. Life's wonderful. One small problem with that is during training time, right? You've got the speech input and you know the words, but you don't actually know which word belongs to which part of the speech, okay? So when you're training a feed-forward neural network, and you're taking this bit of speech, you don't actually know what the target phoneme or the target character should be, right? Does that make sense? Right? You just have words. There's 5 words in a sentence. You've got this enormous chunk of speech. I don't know which part this bit of speech is actually relevant to, right? I don't know which character. So what people did was they were like, oh no, we've got HMMs, okay? So what we do is we run a HMM system on all our training data. And for each bit of speech, we actually know the HMM tells us this bit of speech belongs to this state in our big network, okay? And what we'll do is we'll use that state as the supervision signal for our normal DNN, okay? So that's exactly what they did. Does that make weak sense? Okay, great. Okay, so I know I'm going into a bit more detail here, but I hope it makes sense. So there's just this alignment problem. You don't know which words belongs to which bit of speech. You use an HMM to solve that problem, and then you use the HMM as supervision for your DNN. Okay, and they called this a hybrid model, a DNN HMM. It looks something like this. So you've got your speech input here, your one snippet of speech, and on the output you predict which hidden Markov model state it actually belongs to. And one other reason people really, really like this approach was that they already had these enormous decoders to solve speech recognition. And all you had to do was you basically had to plump out your HMM and put in your DNN, okay, and everything still worked, okay? And people were super happy. Why are DNNs so great? Well, you can really see it as the combination of doing like representation learning at the layers here, followed by a classifier at the top, and it's trained jointly. Okay, you guys know this. Okay, I know this is quick. I hope it makes sense. Okay, so we've done DNNs. We've seen RNNs. Who's left out? CNNs. Sad face. Okay, CNNs also wants to get in on the action. Okay, so why would a CNN actually make sense for speech processing? Okay, let's just go back to the previous slide. What do CNNs give you? Why do we use CNNs for image processing? Forget about speech. Why do we use CNNs for image processing?
Features are local.
Features are local, that's true. Sorry, shared weights, great. So we have less parameters to train. Okay. Yeah, it's hierarchical features, that's also true. It's fast. It gives us scale invariance, right, by max pooling, and it gives us translation invariance, which is related to the weight sharing. Now, the interesting thing is translation and scale actually make sense for speech as well. Here we had a male speaker with the lines very fine on top of each other. Here we had a female speaker with the lines spread out. If you run a convnet on this type of thing, the model could actually learn that these types of features by doing clever pooling are actually the same thing. Okay, so CNNs actually makes a lot of sense for speech as well. Okay, so we've got RNNs, we saw feed-forward neural networks, we saw convnets. Okay, now here's the million-dollar question. Which of those three are actually used by Google and IBM? Okay, so we saw end-to-end models. They're nice. They're relatively easy to train. DNNs, they're good as well. We can plug them into our current systems. And then CNNs, which actually tells us something about what's going on in the speech. Okay, the answer is you use all of them. Okay. So can anyone tell me what CLDNN HMM stands for? Just take a guess, someone. Okay, what's this? Convolutional. RNN, what's another name for fancy RNN? LSTM, DNN, hidden Markov model. Okay, so in 2015 you got ridiculous titles like these. Convolutional long-term taught memory fully connected deep neural networks. And this is the Google paper. Okay, the network looks something like this. You've got convolutional layers. You've got your LSTM layers that kind of builds in the recurrence. You've got your fully connected layers. And then at the output, you're predicting hidden Markov model states. Okay. And actually, if you read state-of-the-art systems, this is what they use. Okay. Now, it's really interesting because end-to-end models are so nice. Why don't we just use end-to-end models, right? We just get speech, audio, we build our models, and it works. So why does this thing actually work better? So I would argue that it's because we're building in more knowledge, more structure of speech. Convnets, we saw on the previous slide, actually makes sense to get scale and translation invariance. Okay? LSTMs make sense because we've got this recurrence built into speech, right? One feature after another. The feed-forward neural networks, with the HMM targets, they actually make sense. So the HMM targets, what we're getting there is really we're putting in some knowledge about the pronunciation of words. Okay. Now, hardcore neural net people would tell you, like Jan LeCun would say, given enough data, you don't need any structure. Okay. It's quite ironic because he developed convnets, right? But he would say, like, given enough data, you don't need it. Maybe that's true, but I don't know how much that is. So I think it's really interesting to think about how we're building in explicit knowledge of the problem into the different portions of our networks. Okay. So speech recognition, I'm done, right? So that's how you do supervised speech recognition. It's super important, right? I went to a talk by a blind guy at Google who showed how he uses the speech recognition and speech synthesis systems on his phone. It's just miraculous, right? 5 years ago, he couldn't do it. So I think it's very important. But at the same time, I think just thinking about speech recognition in isolation is not the right approach. So when you go to speech conferences, there's these hardcore guys. All they care about is speech in, words out. That's it, right? Are you improving my word error rate? Are you getting those words more accurate? And that's it. And I think this is my first rant, and it'll continue for a while. I think we need more interesting studies, okay, that actually looks at speech. We already saw some interesting things here. We saw how our domain knowledge, we actually saw that building in structure into our models actually improves performance. And I think it's very, very interesting to ask, does that tell us something about how we as humans perceive the world and how we process language and speech? Okay. I think speech and language are really like, so people say like bats flying, right? What's their trick? Sonar, right? They've got this amazing ability to send out pulses and retrieve it. The human trick, right, so people would disagree with me, is language. We've got that capability which no other animal has to communicate in this very like fine-grained hierarchical structure and to compose messages in a very, very complicated, infinite way, which I just think is amazing. And we kind of lose that sometimes. So I think it's cool to think how engineering decisions tell us something about what's going on at least in the ear and then maybe in the mind. The other way around as well, I think it's very important to look at psychological studies about where they actually know how we perceive the world and to build that structure into our models. Okay, so for the next part of the talk, I'm going to highlight 3 applications which I think are very interesting and very exciting, where you don't actually need speech recognition to solve the problem. Okay, and in some cases you don't even have speech recognition. So I'm going to mention 3 problems. The interesting thing to think about here is that to build that Google speech recognition system, you need 200 hours of transcribed speech audio. So someone had to go and write that out with 500,000 words of language modeling text. Right? To get this amount of data for all the languages spoken in the world today is impossible. Right? And there's around 7,000 languages spoken in the world. About half of them will die out in the next century or something like that, the linguists will tell you. And a lot of them, I think the majority of them are actually unwritten. You can't write it down. There isn't a writing system. It's just a spoken language. In settings like that, you don't even have the option of doing speech recognition. You can't even train a model because you've got speech, but you don't have any targets. You don't know what the words are. Okay. So I think it's just cool to start to think about these problems and how we can actually help people in those settings where it's very, very difficult to do ASR, or sometimes you just don't need ASR. So very quickly, 3 applications. The first one is things that people at Johns Hopkins University are working on a lot. It's a query by example search system. So I'll say something about this, but people at Stellenbosch have been using the same type of system, so this is where they apply it. They work with the United Nations in Uganda, okay? And for most of those languages, you don't have speech recognition systems. So what they do is they they plant these systems in the field, which records broadcast news, right? So local radio broadcast stations. It records it, it saves it on a server, okay? Now, there isn't a speech recognition system. You can't do anything with that data. So what they do is they build a system where someone can phone in. Say it's a farmer in Uganda, okay? She speaks a language that is only spoken in her local region. We don't have any speech recognizer for that. Now, we've got this system. It records all the broadcast news onto that system. She phones in that system, and in her local language, she says something like crop prices, right? She wants to find out information about crop prices in her area. So she says crop prices, and then what the system does is it searches through this big corpus of audio without using a speech recognizer. It tries to find patterns that look like this crop prices thing, okay? It finds those utterances and it plays it back to her, okay? So she can actually get knowledge of the things that happened recently. This is a very simple example. The UN is specifically interested in tracking disasters in areas like Uganda. So if you have a lot of these stations, okay, and you're able to build systems like this, and maybe not a small snippet, but maybe just build a system that can detect specific keywords, okay? Like, I don't know, malaria, TB, right? Or some of these humanitarian terms. Then you can actually, if you have a lot of these systems and you basically have these things pinging up and down, you can do things like track disasters, track diseases, okay? Which I think is just amazing. And you can do this without having a speech recognizer. You just need to be careful about how you design your system. There's a lot of research going into how do you compare this to actually find these, whole research field, and we're doing some of that work. But I think this is a great application. This is Stephen Bird. He's a researcher in Australia. I think he's also at Berkeley now. I might be wrong about that if this is recorded, but he really likes to travel. So what he would go is he would go into Brazil or some of the areas around Australia and New Zealand, and he would meet with these people that are speaking languages that's dying out. So there's maybe only 10 speakers left. And what he does is he asks them to actually record stories, just tell stories into a mobile phone. So they would just record the speech. Okay? You can't write that down. It's impossible. There isn't a writing system. So what he does is he asks them to repeat the stories in English, okay, for which we have a speech recognition system. Okay? And now you can start to do things like train a model that takes in this unknown language and starts to output English words, right? So you can use that for documenting and kind of cultural documentation, okay, which I think is it's just so super exciting, right? You can kind of it's also a very useful thing for linguists if you want linguists to analyze the language, to give them this kind of these systems that can map from an unknown language to English words, and that can help them browse and search through the data. Last application, so this is at KI Leuven, some of my favorite work. So what they're doing is they're saying, like, in some settings you just don't need a speech recognizer. So imagine you've got a robot in your home, okay? And you just wanted to do a few things, just a couple of things. I don't know, go and open the door for the dog, okay? I don't know, walk to the kitchen. Just a couple of things. So what they said was, well, we don't have a Flemish speech recognizer. So what we'll do is we'll speak to this robot, and then with a joystick actually do the action, okay? And then by just looking at like 6 spoken examples, they will actually learn the mapping from the speech to the action on the robot, okay? Imagine a paraplegic user sitting on a wheelchair, right? They can't move, okay? And just saying forward, forward, forward 6 times, okay? And the wheelchair goes forward, forward, forward. And it learns that mapping from the user's speech to that action, okay? And then turn left, turn right, turn right. In whatever language they're speaking, Afrikaans, Tsonga, okay? And just from a couple of examples, start to learn the mapping of speech to commands. I think this is just super exciting. Just not if you find it exciting. I see people have stiff necks. Okay. So just following on from this, I want to talk very quickly about 2 projects that we're doing in my group in Stellenbosch. Coming back to this problem, right? Imagine you have a big corpus of audio. If you have the words, then you can train a supervised model that takes in the speech and maps that to words, right? You guys can now all build state-of-the-art speech recognition systems and take down Google, okay? But the question is, in a lot of settings, you don't actually have the words, right? You don't have the words. You just have tons and tons of, well, you can collect tons and tons of audio, right? You can plop a system in Uganda, record the audio that's used around it. And what we're really after is a system that can take that audio and find structure in the data automatically. Just look at the audio, find structure in the data, and then acquire language, okay? That's the ideal, okay? Do you think this is possible? If I just give you tons and tons of audio and I ask you, learn this language, do you think it's possible? I don't actually know. I honestly don't know what the answer is. But we have an example of one system that can do this. Sorry if you've seen the talk before, because you've seen the system as well. We've got an example of one system that can just take raw audio and learn language. What's that system? Right, I'll put up a circuit diagram. Right, so humans, right? You take a baby, you plump them into a new linguistic environment, you leave them to train for 2 years, okay? With the right learning rates and everything. After 2 years, it can understand language almost perfectly. After 4 years, it can speak almost perfectly, okay? That is just amazing. If you just think about that just for a second, it's people go on about AI taking over the world. We're so far away from building systems that can do that, okay? And I think Jacques also mentioned this. I think this is where the interesting stuff lies. How can we find data how can we find structure in raw data? Okay, and we haven't cracked that problem. So I'll quickly talk just very, very quickly about the systems that I'm working on, that we're developing. So here's the problem. I give you a whole bunch of raw audio. Okay, you don't know which words are used. You don't know where words start and end. You just have raw audio. That's it. Okay. What I want is a system that takes that audio and converts it into something like this. I want a system that can chunk up the speech and say, I don't know anything, but I think this is where a word ends, and this is where a word ends, and this is where a word ends, okay? That's called segmentation, breaking up the speech stream into words, okay? And then I don't know what this red thing is, right? I don't know anything about words, but I think this red pattern, I think it reoccurs there and there and there in my data, okay? Or this green pattern, I think these 3 things, I don't know the identity of those things, but I think they're the same word, okay? And that's clustering. So you've got this joint segmentation, breaking it up into words, and then clustering problem, basically grouping the words together to form clusters, okay? I don't want to go into the detail, but this is our model for doing this. Very quickly, you start with speech, you extract features. Actually, what we do here is we use autoencoder, unsupervised neural network, to do the feature extraction for us. So we don't just do FFT, we do autoencoder. Okay, that gives us nice features. Really shouldn't go into the detail here, but I'll do it anyway. When you start out, you don't know where words start and end in the speech stream. So what you do is you just guess a few boundaries. Okay, you just guess. Okay, there and there. Okay. Now, given those boundaries, I won't go through the step. If you think these are the boundaries, you can actually go and train a supervised model to segment and cluster the audio. Okay, that model will be crap. Okay, it will be very, very, very bad. But what you can then do is you can take that model and you can say, well, under that model, what is a better positions to put my word boundaries? Where are better positions to put my word boundaries? You can put the word boundaries there, go up again, update your model parameters, and what you do is you cycle this thing, down, 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 okay, until it converges. Okay. And then what you hope is that the stuff that it discovers, you hope that it put boundaries at the right places, and you also hope that the words were grouped together correctly. Okay, now I'm going quick. So we've built this system. It took me 2 years of my life, right, for my PhD. It's quite embarrassing, but that would be the first bullet. So that bullet took 2 years, and then these 2 bullets took another year. Okay, this is super upsetting. Okay, so what we did was we built this model. We took a whole bunch of audio and we passed it at the model. Now you want to know, is this model working? How would you do it? Huh?
Put an only spoken language in.
Okay, that's right. Yeah, you can take English data, you can put that into it, and then you can evaluate the model. That's one thing we did. To get a very quick idea of how the model is performing, this is what we do. We ask it, okay, you've segmented and clustered all these words. You've grouped these words together. Play me your biggest cluster. Take the biggest word in your data set and basically go and find all the snippets in your data that corresponds to what you think is a word. And what we'll do is we'll quickly play them one after the other. If they're all the same, then we know that that word is a sensible word. If they're different, then our system's screwed up. Okay, does that make sense? Okay, so for 2 years, I worked on a very, very small domain problem, read digit sequences. So this was people reading telephone numbers, 08256514452. Okay, so crap, I just gave my telephone number. Anyway, it's not. It's not my telephone number. Okay, so read digit sequences, and there's only 11 words in that language, 0 to 9 and 0. Okay, go and count it. 11 words. So we know how many words there should be. We run the model and we ask it, play back your biggest cluster, play back your biggest group. Now, I've got no idea if the audio actually will work in this room. So this is what we got.
0, 0, 0, 0, 0, 0, 0.
Okay, so the crap quality is this room, okay? But it makes the system even more impressive, right? If you could detect that word in that noisy speech, I would be super happy. Okay, but it was actually clean speech, full disclosure. What was the word? 0, so it learned that word. Okay, then for another year, I actually that's a very small language. We then ran the system on a large vocabulary language. We took American English. What's the most common American English word? Okay, that's a good one. Like. I can't actually remember what. Okay, so let's just. I is a difficult word because it's pretty short, and in sentences it bleeds. But okay, so anyway, here's the biggest cluster that we found. Okay, and then the last thing, we also ran it on a Tsonga data set. So Tsonga is a South African language, one of our official languages, and we just ran it on that data set as well. Any Tsonga speakers here? I gave part of this talk to my Systems and Signals class, and I was so happy. It was the first time there were actually a Tsonga speaker in my class, and he could tell me what the word means. Anyway, so this is the Tsonga, one of the biggest words. So the word is fanele. I think it is something like, he says it is like. When you say this is like this, fanele, that's the meaning. Same system, these two. Same system, which I think is just very, very cool. Okay. Okay, there, I flashed it. Okay. So who has seen this movie, Arrival? Who hated it? You can be honest. Okay, so there's like 2 honest people in here. I really liked it, but the first time I showed this slide, it was an American audience. And in America, people either hated it or loved it. Okay, I've got 5 minutes, so I'll go through this very quickly. The one problem with what I said was, like infants, what happens is we're bombarded with just audio, okay? But that's not true. Infants actually have another signal well, they've got tons of other signals, but basically what they do is they hear audio, okay? And then they also have this visual context of what's happening in the audio. And in this movie, I won't spoil it for those who haven't seen it, go and watch it. There's this linguist, Amy Adams, is that her name? The actress. She plays a linguist. They come to her, the government comes to her, and they play her an audio snippet. And it's like some weird noises. They ask her, you're a linguist, tell us what the words are. And she's like, no, I can't do it. I need context, right? And so then they take her to the native speakers, and they get a bit of context, okay? Specifically using images. That's actually what they do. Okay, so I really like this movie. I pivoted my whole research agenda that way. So here's the question. We just learned from raw audio, but what if you had audio untranscribed and it's paired with an image, right? So you would have a sentence like this. A winter landscape with 4 people in the snow. And the question is basically, does this image help us to better process, to better discover words in this, in the speech without actually having transcriptions for that? I think this is very, very cool. Okay, so I won't go into that much details. When I started with this work, these guys at MIT, they started at the same time, David Harworth and Jim Glasscoop. Awesome work, really, really awesome. So their idea, very quickly, is basically you've got this paired speech and image, you map them into the same space. You process this with a convnet, you process that with a convnet. If you fancy, you can use an LSTM somewhere. You basically summarize the speech with a single vector. You summarize the image with a single vector. And then what you do is you basically say these 2 vectors for that paired image needs to be the same. If you train a model like this, you can basically search for images using speech without using speech recognition, or search for speech using images, right? So I think this is super exciting. Our model worked slightly differently. So our model was actually able, after training, we trained on this, we could spot keywords in speech. So you train a model with images and speech, and then you say, okay, I've trained my model, go and find me all the utterances containing the word beach in my corpus, okay? So I know that's quick. I quickly want to just play you some examples of, I've got 2 minutes, so I won't play it, I'll just read it, okay? So we trained a model on images and speech, and then we asked the model, after training, here's a corpus of audio. Find me all the utterances containing the keyword beach, okay? And what we'll do is, we'll just look at the top 10 utterances that this model retrieves. So the keyword was beach. I can play you the audio. Maybe I'll do that very quickly.
A boy in a yellow shirt is walking on the beach holding a surfboard.
Right, so it correctly detected beach. Trained without any transcriptions. Okay, so that's correct. Behind, weird keyword, we make a mistake. This is the top retrieval from our system. Bike, a dirt biker flies through the air. It's pretty good. Okay, it's not exact match because that's biker and not bike. Here's the interesting one, boys. Okay, I won't play it. But the utterance was, 2 children play soccer in the park. Okay, what's cool about that? Right, so I've got 1 minute. Boys is not children, it's a mismatch, okay? But obviously boys and children are semantically related in some way, okay? Large, here we had a rocky cliff overlooking a body of water. Presumably the rocky cliff or the body of water is large, right? A whole bunch of interesting, yellow, this one is really interesting, a tan dog jumping over a red and blue toy. That's clearly a mistake, but what's happening is, because the system is learning from audio and the visual context, you basically get that match where there's a lot of colors named here. Okay, let's wrap up. What did we see today? We saw 3 things: state-of-the-art speech recognition, and then we saw 2 rants, right? Basically saying that we need more studies that really focuses on the interesting stuff in speech. I think speech can tell us something about language, and I think one of the big problems to crack is how do we process, how do we acquire language, okay? We might not be able to build models exactly in the way that the brain does it, but we might be able to include some of the computations at least at kind of a software level about what's going on in the mind. And I think that's really cool. Specifically in my lab, I think there's still a lot of core, hard machine learning problems, specifically unsupervised machine learning problems to solve. I think it would be great to build more systems specifically for South African languages. We're here and we've got this opportunity that there's one of the few populations on Earth that speak so many languages in the same geographical area. Very rare. I think it's also very interesting to think, what can vision tell us about speech and what can speech tell us about vision? We know how some of the processes that we humans use to process vision, and does that carry over to speech? What can we learn about language acquisition in humans? Do these models tell us something about how we as humans acquire language? And then I'm really keen to put more of this stuff into this BB-8, into robots. Main takeaway, look at machine learning problems, not just from the supervised angle, tons of data, but really try and look at it from a different perspective. Okay, there's most of the code is here, and that's my website. Okay, thanks a lot. Can I take one question?
Yeah, there's time for questions. Thanks so much. Anyone that has questions, please ask.
Yeah, Shane.
Yeah, I was thinking about that network where they take the image and the audio and then get those 2 vectors and compare the distance between them. Do you recall how that distance was defined?
I don't know if it's in a backup slide, but basically it's something like that. So there's the image, there's the speech, you map them, and you want to figure out that distance. No. So that's what a lot of us started out doing. Euclidean, we found cosine worked better, but the best thing to do is a hinge loss, a contrastive loss. So basically what you do is, you've got this image, you've got this speech, you actually take another example of speech, and you say that this image and this speech needs to be closer together by some margin than the random noise example there. I can explain that again afterwards, but it's a hinge loss. Okay, so you basically say these 2 examples, and we've got an adversarial example, and we want to push these 2 together so that they're more closer together than this 3rd example.
Okay, well, I'll ask a question if no one else has one. What's one of the biggest challenges you run into doing this sort of work?
You mean in terms of actually implementing the models?
Yeah.
Well, this is a stupid answer, but debugging is really, really hard. Because what can happen with these types of models is the model can actually start to learn. So when you debug, right, you build your model and you look at your error rate, and you're like, ugh, it's not going down, okay? But what can happen with these models are that it can actually start to learn things which is not in your error rate, but is actually sensible because it's unsupervised. So one example is, in our digits example, the model learned 2 clusters for the word 8. Okay, so it had 8 and A, because in context you won't actually say the t in the end of 8, right? If that makes sense, right? And 9 and 5 both have the vowel I, okay? And it would start to create a cluster for that specific vowel. This isn't wrong, right? But when you actually look at your score, you're like, ugh, my model is broken, okay? More hacking. And I think evaluation is a big problem. And debugging, actually knowing whether your code is working. Yeah.
Basically, where do you start with debugging? With the semantic part or with the error part?
Where do you start debugging? I think you start somewhere early on. What you do is you just listen to stuff. That's what I do. I look at output, okay? Well, okay, now before that...
Your outputs were semantic.
Yeah. So that was just because we did an error analysis. He's talking about this slide, right? Actually, the first time we calculated the metrics here, we were like, oh, our system is really crap. It gets like 55% accuracy, which is cool for a system without supervision. But then we actually looked at the errors, and we're like, oh, this isn't a bug, it's a feature, right? So if you're, I don't know, if you're the US if you want to spot keywords in speech, you might not just be interested in that specific keyword, but also related things. You're not just interested in disaster, but also hurricane and tornado, which might all map to the same thing. Okay, debugging, you start by looking at the loss. If the loss doesn't go down, then you know you're broken. Then you start to look at output. Okay, if your output starts to look sensible, then you're very happy. And then you start to play around with metrics, and then you optimize your metrics on tons of GPUs. If you have some, I don't, so I just report the loss number. Okay.
How do you deal with bias? So, for instance, if you're using lots of audio text from, say, American English, which is what there's more of available, but then you want to check it against another variant of English, will it just not, how do you deal with it not recognizing it because it sounds different?
Yeah, so the short answer is it just won't work. And it's a super important problem. People make these claims of AI generalizing. It's very, very difficult. It will do something, but the problem is if you have things that's just similar enough, you know, like Scottish English, like have some very weird things in there, okay? And then it will just misidentify it. And with these systems, for example, you'll see we trained on natural scenes, right? We trained on pictures that looks like scenes like these. And you see that evaluation is also done on that type of data. If we used another corpus, we probably would have had much worse scores, but this is a fundamental machine learning question, actually. And in the end, the answer is you need to get data from that variety of English.
Thanks, great talk, very interesting. I wanted to know, so the brain is actually notoriously bad at hearing what people say.
Mm-hmm.
And that's why often if you meet a new person, they say something, even a word that you've encountered many times, they'll say it slightly differently and it'll take slightly longer for you to process it.
Mm-hmm.
Because we do inference
Mm-hmm.
on, they probably said that based on what they said afterwards.
Yeah.
How much inference have you done in your speech work?
Okay, so there's so many questions built into that, right? What you're saying is exactly true. When we hear speech, we're getting visual context, right? It's very interesting. Sometimes you hear something, right? You can walk away, you misheard it. You walk away, and in your head, you kind of do this weird rescoring thing, right? It's language model rescoring. You take your NBIS list, you rescore it, right? And then you're like, oh, that's what the person said, and then you move on. It's miraculous. So, okay, I didn't answer your question. When you build in vision into your system, then of course you're taking in more context than just the speech, okay? In this model, one thing we did try was to, when you cluster this word, decide which word this one belongs to, you actually look at the preceding clusters and you say, well, this sequence of inferred words, they kind of hang together. And then because I know that this word happened here, then this word here is more likely later on, which is exactly what you're describing. It's a language model. That actually didn't work that well in this system. And I think the reason is just the performance of that system, the mistakes it makes in the clustering is quite big. And for example, in digits, there aren't really, like if I say a O now, then it doesn't really tell me what's going to happen later on. But it's very important. And in speech recognition systems like Hardcore, they build a lot of that knowledge through language models, right? So if you train a language model on Wikipedia, you build in that knowledge about which words hang together. And there's some very cool studies, I think by people at CMU, which build supervised systems that also has a camera, right? So you're scanning the scene in which someone is talking with a microphone, and by combining those two signals, they actually get improved speech recognition performance by getting that context. If you want that citation, I think Florian Metzer is one of the authors, but you can email me.
I think that's all we have time.